What is a heap? When we talk about the heap, we usually talk about the binary heap. In this video, I'm going to explain what a binary heap is and its array implementation. There are three properties about a heap. Firstly, a heap can be seen as a binary tree. In a binary heap, each node has at most 2 children. It cannot have 3 or more children. Secondly, a heap must be a complete tree. What is a complete tree? It's a tree filled from left to right, from top to bottom. Now I'm filling from left to right. Whenever you pause this video, what you see is a complete tree. You cannot fill in the next level if the current level is not full. This is complete. Even the last level is not full. Of course, this is complete too. This is not a complete tree, since the last level is not filled from left to right. This is not. So actually, what we can miss is only the last few elements at the last level. Let's take a look at the last property, the value. In a heap, each node has a value. Heap organizes these values in 2 ways. It's either a max heap or a min heap. If every node is larger than or equal to both children, left child and right child, we call it a max heap. If every node is smaller than or equal to both children, left child and right child, we call it a min heap. If we find an exception, we say this heap is not heapified yet. It needs to be rearranged to meet the property. Can we conclude that a heap is always sorted? Nope. In this max heap, 7, 4, 5 in the last level are not in ascending order. Can we conclude that every level must be larger than the next level? Nope. In this max heap, 6 in the second level is smaller than 7 in the last level. So the only principle that we can rely on is to compare each node with its children. There's no shortcut. Okay, remember the 3 properties of binary heap. Next, let's talk about array representation. To implement a heap, we use arrays. That is to say, each heap can be represented by an array. Why use arrays? Because we can easily find out the parent and children of any element. I will explain this later. Here is a max heap, and if we flatten this heap from left to right, top to bottom, we'll get an array A, 9, 8, 6, 7, 4, 5. Or we can write the array index above each node. The array represents a heap, so that we don't have to draw the heap every time. With the help of the tree, we can see that the parent of 7 is 8. The parent of 8 is 9, and so on. Now, did you find any pattern between the indexes? Or let me ask you 3 questions. My first question is, given any index I, what is ai's parent? We do not have to draw the heap to figure that out. The answer is the floor of I minus 1 divided by 2. What I mean here is that when we are standing on the ith element in an array, our parent is this. This is guaranteed. Well, I do not always believe tricks, so I want to validate it. I'll validate every node as long as it has a parent. Here is a validation table. Everything filled in this table should be the index, not the value. When I'm saying node 1, I mean the index is 1, not the value, okay? For node 1, the parent should be node 0. This is the correct answer. Now let's hide the heap and see if our formula works. Put I equals to 1 in the formula, we got 0, which is correct. Yeah! Okay, let's move on. The next node is node 2. Don't confuse value with index. For node 2, the parent should be node 0, which is the correct answer. Now let's hide the heap. Put I equals to 2 in this formula. We got 0, which is correct. For node 3, the parent should be node 1. Now put I equals to 3 in this formula. We got 1, correct. For node 4, the parent should be node 1. Now put I equals to 4 in this formula. We got 1, correct. Finally, for node 5, the parent should be node 2. Now put I equals to 5 in the formula. We got 2, which is the same with the correct answer. Okay, now given any I, we will be able to know who is a parent without any join. Cool? Now, let me ask you the second question. Given any index I, what is I's left child? The answer is 2 times I plus 1. What I mean here is that when we are standing on the ith element in an array, our left child is this. This is guaranteed. Now, time to validate. For node 0, the left child should be node 1. This is the correct answer. Now let's hide the heap and see if our formula works. Put I equals to 0 in the formula. We got 1, which is correct. For node 1, the left child should be node 3. Now put I equals to 1 in the formula. We got 3, which is correct. For node 2, the left child should be node 5. Now put I equals to 2 in the formula. We got 5, correct. Okay, now given any I, we'll be able to know who is the left child without any join. Now, let me ask you the last question. You might already know what I will ask about. Given any index I, what is I's right child? Can you guess? The answer is 2 times I plus 2. What I mean here is that when we're standing on the ith element in an array, our right child is this. This is guaranteed. Now, time to validate. For node 0, the right child should be node 2. This is the correct answer. Now, let's hide the heap and see if our formula works. Put I equals to 0 in the formula. We got 2, which is correct. For node 1, the right child should be node 4. Now, put I equals 1 in the formula. We got 4, which is correct. Okay, now given any I, we'll be able to know who is the right child without any join. Let's do a summary. Now, given any I, what is a parent? Floor of I minus 1 divided by 2. What is a left child? It's 2 times I plus 1. What is a right child? It is 2 times I plus 2. They will be very helpful when you implement the heap. Although drawing is also helpful, if you have a heap of 1,000 nodes, the graph will be too big to draw. Without the help of the drawing, we can easily find out the relationship by using the formula. Okay, I have a gift at the end of this video for you. You're encouraged to leave your answers or questions in the comment. See you later!